This video is on the Bohr model, quantization of energy levels and angular momentum. Question number 1. Use Newton's second law of motion, the equation for total energy, the equation for angular momentum, and the assumption that the angular momentum of an electron orbiting a hydrogen atom is quantized to derive the equation for the energy of an electron orbiting a hydrogen atom. So this equation is incredibly important in physics. So let's see how it was obtained. So remember, in linear momentum, P equals mv. In angular momentum, L equals r cross P, which is rmv sine theta. So for the orbiting electron in the hydrogen atom, assume we have one proton in the middle and one electron orbiting the hydrogen atom. We have F equals ma, which is kqqq over r squared. We know the acceleration in circular motion is v squared over r. So the electron is moving in a circle. So the mass of the electron times v squared over r is equal to kqqq over r squared. Q for the electron is equal to Q for the proton, which is 1.6 times 10 to the minus 19. So we'll just call that E. So Q electron, Q proton becomes E squared. Simplifying this equation, we're going to get mv squared equals ke squared over r. Okay? So I highlighted this equation in yellow because we're going to come back to it, hopefully. Remember, this whole time we're going to be talking about an electron in a hydrogen atom. So we just used the force equation, Newton's second law. Now let's look at the energy equation. The energy of the electron is its kinetic energy plus potential energy. So its kinetic energy is 1/2 mv squared. Its gravitational potential energy is minus kqqq over r. Qq simplifies to E squared. What is mv squared equal to? Well, mv squared is here, ke squared over r. So let's substitute that ke squared over r here. And now we have two fractions here. If we get the same denominator, we get minus ke squared over 2r. So the total energy of an electron going around a proton in a hydrogen atom is minus ke squared over 2r. Now the reason why it's negative is because the electron is not free. If the electron was moving in a straight line, then the energy of the electron would be positive. But the energy of the electron is negative because it's bound. Okay. So this is a big jump here. Assume that the angular momentum is quantized, just like energy can be quantized. So mv squared equals nh over 2 pi. So the angular momentum is a integer n, which could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, times h over 2 pi. So let's square both sides of this green equation. And then let's solve for mv squared. We get this. Okay? So in yellow here, I have an mv squared. And then up here in yellow, I have an mv squared. So what do you think we should do? We're going to set both of them equal to each other, the two yellow equations. So this above equation in yellow is equal to the force equation in yellow. Okay. So when you set the two yellow equations equal to each other and you solve for r, you get about 0.5 times 10 to the minus 10 meters times n squared. So everything in this parentheses here, h bar squared divided by 4 pi squared e squared km, m is the mass of an electron, all of that is equal to about 0.5 times 10 to the minus 10 meters. So let's plug in the above equation into the energy equation. So let's plug in this R into the energy equation, which is here. So we get this. So the energy of an electron in a hydrogen atom is about minus 13.6 electron volts divided by n squared. If n is 1, we're at the ground state. If n is 2, we're at the first excited state. If n is 3, we're at the second excited state. You get the point. Okay. So this equation tells us that the energy of an electron in a hydrogen atom is quantized, discrete. Okay. So question 2, what's the significance of this equation? Because we have the n squared, it shows us that the energy of the electron in the hydrogen atom is discrete or quantized. It's not continuous. Question 3, determine the radius of the 3 lowest energy levels of an electron in a hydrogen atom. Well, let n equal 1, 2, and 3. So we got the ground state n equals 1, the first excited state n equals 2, and the second excited state n equals 3. Question 4. Complete the following table for the 4 lowest energy levels of an electron in a hydrogen atom. So we have this table. Got to fill out the table. So for electron volts, we're just going to let n equal 1, 2, 3, and 4. And then for the energy in joules, we have to convert from electron volts to joules. So ta-da, we get the result here. So you could see as the electron gets in a higher energy level, the energy of the electron increases, because this is minus 2.18 and this is minus 1.36, which is closer to 0. Question 5. Determine the gain in total energy in electron volts when an electron jumps from the first excited state to the 5th excited state. So it looks like here we did minus 13.6 eV divided by 6 squared minus 13.6 eV divided by 2 squared. Question 6. Determine the gain in total energy in electron volts when an electron jumps from the ground state to the 3rd excited state. Once again, this is minus 13.6 eV divided by n squared minus 13.6 eV divided by n squared. Question 7. Describe the Bohr model of the atom. There is an atomic nucleus which exists in the center of the atom, which contains neutrons and protons. Electrons travel around the nucleus. The electrons' orbit radius and therefore energy are discrete and can only take specific values. The energy of the electrons in an atom is quantized. Electrons in the atom can transition to higher energy levels or to lower energy levels. That's called photon absorption and photon emission. So remember this image. From the previous video and worksheet, we looked at the Thomson plum pudding model. Then we evolved to the Rutherford model, and now we're at the Bohr model.